Good morning, dear students. My name is Ferhan Mazher, and today is 21st of the April 2021. Right now, I am with the 11th cabbage class, and the subject we are studying is Physics 5054. It's O levels physics. Today, we have set our heart to solve October-November 2017 2-1 paper. It's a theory paper. We call it paper 2. In this session, in this video, we will be solving the section A of this paper. And the section B of this paper I have already solved and it's uploaded in the YouTube. And if you go on to my playlist, and there you can find the paper 2, zone 1, section B. The name of the playlist is. And there you can find the section B of this paper. So let's start today's paper. And here we go. We have the first question coming onto your screen. So October, November 2017 to 1, section A, we will solve in this session. So figure 1.1 shows a painter standing on a wooden plank directly above the right hand support. The plank has a length of 3.6 meter with 0.35 meter and the thickness of 0.025 meter. The gravitational field strength G is 10 Newton per kg and the mass of the plank is 23 kg. So this plank's mass is 23 kg. Calculate the density of the wood from which the plank is made. If you want to find out the density of the plank, it's very simple. We know the length, width, and the height, thickness, I mean. And you can find the volume. The volume is equal to length into width into height. And once you know the volume, we know the mass of the plank, that's 23 kg. And once you know the mass, the volume, apply the formula density is equal to mass divided by volume. So I've done this on a paper. Let me show you. So on your screen, so this will show up. Okay. So the question number 1, volume is length into width into height equals to 3.6 multiplied 0.35 multiplied 0.025, and the volume will be 0.0315 meter cube. The mass is given, that's 23 kg. And you want to find out the density. Density is equal to mass divided by volume. That will be 23 divided by 0.0315. And the answer will be 730.16 kg per meter cube. It's a 2-mark question. So let's have a look at the marking scheme and see what the marking scheme says. Okay, so the marking scheme is showing on your screen. The marking scheme says, see the marks also. The density will be 730 kg per meter cube. It's a 2 marks numerical, very simple, straightforward question. Okay, so let's move to the next part, and the next part is the center of mass of the plank is in the middle of the plank at a distance of 1.3 meter from each of the support. Calculate the weight of the plank. Okay. So the weight of the plank is question. We know the mass of the plank. So weight of the plank, W is equal to mg. Just apply that formula, do the calculation, you will get the answer. I've done this on a paper. W is equals to mg, B first part, and the mass is 23 kg. The mass of the plank is 23 kg multiplied 10, and that will give you 230 Newton. So the weight of the plank is 230 Newton. So let's have a look at the marking scheme, what the marking scheme has to say. So B first part 230 Newton is the answer. So our work is right. Our calculation is right. Okay, the next question, the moment of the plank about the right hand support. The moment of the plank about the right hand support. Let me go back to that diagram. So here the weight is acting, which is acting downward. and that is, you know, 230 Newton. The weight is 230 Newton. And from the right hand, the distance between this support, this pivot on the right hand, and the line of action of the weight, the perpendicular distance between them is 1.3 meter. So I can calculate the moment. The moment is equal to the weight multiplied its moment arm, and that will be 230 multiply 1.3 meter. 230 Newton multiply 1.3 meter. I've done this on a paper. Let me show you. So moment is equals to F multiplied D. That's 230 multiplied 1.3. That will be 299, and approximately this will be 300 Newton meter. 300 Newton meter. By mistake, I wrote this M capital. This M is basically lowercase. 230 Newton meter is the answer, so our answer is right. So let's go to the next question. The painter moves further to the right along the plank, and the plank rotates about the right hand support. Explain why the plank rotates. Let me show you. So what they're saying? They're saying this man right now is standing. The point where he is standing, that's exactly over the support. So the line of action of the weight of this painter is passing through the pivot. So his weight will produce no turning effect. The reason is its moment arm is 0, because he's standing exactly over the pivot. So that's why his line of action of the weight will pass through the pivot, and obviously his distance from the pivot is 0. So the turning effect produced by the painter, that will be 0. But what he says that the painter moved to the right. If the painter will move to the right, you see what will happen. His line of action will be no more passing through the pivot. His line of action is the line of action of the weight that will be passing. That will be on the right side of this pivot. So now this man is the weight of this man will also produce a turning effect. So when he will produce turning effect, his turning effect will be clockwise. So this plank is supposed to tilt or fall towards the right side. So let me check what I have written. I have written the answer. Let me show you my answer.
Sir, which paper is this?
This is October-November 2017 2-1 paper. Section A we are doing. When the painter moves towards right on the plank, his weight produces a clockwise moment, which disturbs the equilibrium of the plank, and it will tilt towards right. So when the painter moves towards right on the plank, his weight produces a clockwise moment, which disturbs the equilibrium of the plank, and it will tilt towards right. So let's check the marking scheme. What the marking scheme has to say. Okay, so on your screen, question number 1, C part. Moment of the painter, clockwise moment about the sport is greater than, not equals to, the different from the moment of plank anti-clockwise moment. So now the clockwise moment will be more than the anti-clockwise moment. That's why the plank will turn to the right. So that was question number 1, C part, and by this we are done with the question number 1. So let's move to the next question. The next question is question number 2. So here we go. He says that the figure 2.1 shows a can of compressed air that is being used to blow dust off a computer keyboard. So you have, in this can, we have compressed gas, and when you press the button, that gas comes out, that air comes out, and it is used to clean the objects like the keyboard of the computer. The pressure of the air inside the can is greater than the pressure of the atmosphere. State what is meant by the term pressure. You see, when you apply force on an object, then the force per unit area, that is known as pressure. So the force exerted on unit area, that is known as pressure. It's a 1 mark question. I have written this answer. Let me show you my answer, and then we will see. Okay. So question number 2, A part, pressure is force acting on per unit area of the surface. So on a surface, the pressure is force acting on per unit area. That's pressure. So let's check the marking scheme. What the marking scheme has to say, it says the pressure is force divided by area. 1 mark question. Very simple and straightforward question. Explain in terms of molecules why the pressure of the air inside the can decreases as it is used. You see, when you use the can, you press its button, and what happens that the air molecules come out. Now, the air which is left inside, the number of molecules which are left inside the can, that number decreases. For example, if there are, suppose there are 100 molecules in that can of the air, when you press the button and some of the air molecules will come out, and what will happen, for example, 20 molecules came out. Now there are only 80 left inside the can. So the mass of the gas which is inside that can, that has decreased. So when the less number of molecules are left inside the can, so obviously this will, the molecules colliding with the walls of the container, the number of molecules colliding with the walls of the container, that will decrease. The reason is because now there are less number of molecules left inside the can. So that's why the pressure is supposed to decrease. It's a 3 mark question. Let me show you my answer, and then we will check the marking scheme. When can is used, air molecules come out of can. So number of air molecules in the can decreases. Now there are less number of molecules per unit volume inside can. The frequency of collision of air molecules with the walls of can decreases. Due to this, less force is exerted per unit area of the walls of the can. So now there will be less collisions per unit area because there are less molecules present in the can. So less force is exerted per unit area. So the pressure will decrease. Let me check the marking scheme. What the marking scheme has to say. Marking scheme says, question number 2A, second part. Fewer molecules or less gas or more space further apart. Less frequent collisions with the walls. Less force exerted on the wall. It's a 3 mark question, and you can see that the 3 main points which must be there is that there are fewer molecules, less frequent collisions with the walls, and less force exerted on the wall, because there will be less collisions per unit area, so there will be less force exerted on per unit area. That's why the pressure will decrease. So I hope you will be able to write this answer. Let's move to the next question. A student uses an inverted measuring cylinder in a water trough to measure the volume that the air occupies at atmospheric pressure. Figure 2.1, 2.2 shows the equipment. So here you have a can that has air inside it, compressed air. And here we have a trough, and in this trough we have water. And I have an inverted measuring cylinder here. And we will exert here through this pipe into this measuring cylinder. As you will release the air from the can into this cylinder, the air bubbles will come here and they will push this water downward. Initially, the inverted measuring cylinder is full of water. The student presses the top of the can and air passes through the rubber tubing into the inverted mining cylinder. The air gradually replaces the water in the cylinder until no more air can leave the can. Final temperature of the air is equal to its initial temperature. The volume of the air inside the can is 1.8 expo minus 4 meter cube. So the volume of the air inside the can is given. And the temperature will not change. He said the temperature will not change. The student observes that at an atmospheric pressure of 1 expo 5 Pascal, the total volume of the air in the mining cylinder, the can and the tubing is now 9.4 expo minus 4 meter cube. Determine the original pressure of the air in the can. We know the V1 value, that is 1.8 10 per minus 4 meter cube. I don't know what is the pressure 1. I want to find out that. The pressure number 2 is given, that's 1 expo 5 Pascal. The volume 2 is given, that is 9.4 expo minus 4. So because the temperature is constant and it's air, it's gas, so I can apply the formula P1 V1 equals to P2 V2. The value of the V1 is given, the value of the P1 is questioned, the value of the V1 V2 is given, the value of the P2 is also given. A very simple and straightforward numerical. It's a 2 marks numerical. We want to find out the P1 value, the pressure of the air in the can. So let me show you how I have done this. It's very simple numerical. So let me increase the sun. Okay. So P1 V1 equals to P2 V2. P1 is question. V1 is 1.8 expo minus 4. P2 is 1 expo 5 and the V2 is 9.4 expo minus 4. Just rearrange it. P1, make the P1 subject of the formula, and the P1 value, the final value will be 5.2 expo 5 Pascal. A very simple textbook kind of numeric. Easy, without any difficulty. So let's check the marking scheme. What the marking scheme has to say. So our answer is 5.2 expo 5 Pascal. So our answer is right. So this was the question number 2. Now we are moving to the question number 3. So here we go. Unwanted gold jewelry is heated in a furnace until it melts. Figure 3.1 shows the liquid gold being poured into a mold to make a gold bar. The melting point of the gold is 1100 degrees centigrade. State 2 ways in which the molecular structure of gold at 1200 degrees centigrade differs from its structure at 1000 degrees centigrade. Okay, so try to understand this statement. When the gold will be at 1200 degrees centigrade, on your paper you can write, when the gold will be at 1200 degrees centigrade, the temperature is higher than this melting point, so it means that the gold will be liquid. And when the temperature is 1000 degrees centigrade, it's lower than the melting point, so the gold will be solid. So the basic question is the difference. Now I can read this statement in a different way. State 2 ways in which the molecular structure of the gold at the liquid, as in the liquid state, differ from its structure at the solid state. So basically you have to write the difference between the liquid and the solid. This is the basic question. You have to write two differences. He wants you to write about the molecular structure. You see, at 1200 degrees centigrade, when the gold is in the liquid state, the molecules will be moving. They will be not fixed in a position. They will be not arranged in regular patterns. So these are the two basic structure. When the gold will be solid, the liquids, the particles of the gold, they will be fixed in position. They will be fixed on the lattice, crystal lattice, and you can say that they will be only they will be in the fixed position. They will be only uh, allowed to vibrate, but if we don't want the vibration thing here, if we just want to talk about the structure, the pattern of the gold molecules in the solid state will be regular, but in the liquid state it will be not regular, it will be random. So let me show you, it's a 2-mark question. Question number 3A part, I've written this answer. So let me show you my answer and then we'll check the marking scheme. Irregular arrangements of gold molecules at 1200 degrees centigrade. Intermolecular distances are greater in the gold at 1200 degrees. The distance between the molecules when the gold is liquid, their intermolecular distances will be larger. So these are the two differences, and let's check what the marking scheme has to say. Very easy differences. Let's see what the marking scheme says. He says you can write from any of these, any of two of the following. Irregular arrangement of the molecules. Intermolecular forces weaker, not held as firmly together. Intermolecular distances greater, more spaced out. Move in clusters through the liquid, not just vibrations or positions. Not fixed or can slide past each other. So these are a lot of differences between the gold in the liquid state and the gold in the solid state. So you can write two of them. It's a very easy and very, very famous question. The difference between the liquid and the solid, the molecular structure difference. So let's move to the next part. In the furnace, 0.84 kg of the solid gold reaches its melting point. The furnace continues to supply thermal energy, and after a short time, all the gold melts. Explain in terms of molecules why thermal energy is needed to melt the gold. Once you have attained the melting point, and then the gold will start melting, you need to continue providing the thermal energy. And on the melting point, when you provide the thermal energy, that energy is used to break the intermolecular bonds, to overcome the intermolecular forces, and to move the molecules away from each other. And none of this energy is used to increase the kinetic energy. Never, never, because here a state change is taking place. Never say that this energy is being used to increase the speed, because the speed of the molecules is not increasing. Kinetic energy of the molecules is not increasing. Yes, their potential energy, intermolecular potential energy is increasing because they are moving away from each other. Now, another word you can add is that the latent heat of fusion, the energy which you give, that is being used as the latent heat of fusion. So let's check my answer and then we will see what the marking scheme has to say. Okay. Energy is needed to melt at melting point because energy used to overcome intermolecular forces, break intermolecular bonds, and move gold molecules away from each other. It's a 2-mark question. So this is my answer. Let's check the marking scheme, what the marking scheme has to say. Question number 3B, first part. On your screen, work done or forces overcome. Atoms pulled apart or bonds broken. So I think our answer is right. So let's move to the next part. He says that the specific latent heat of fusion of the gold is 64 kilojoules per kg. It's not just joules. He says kilojoules per kg. Calculate the thermal energy supplied to melt all the gold. We know that how much gold we need to melt. 0.84 kg. And its specific latent heat of fusion is also given. So if its specific latent heat of fusion is given, so you can very easily find out. You can very easily find out the total amount of heat required. You see the total amount of heat required. You can calculate. The formula is very simple. The formula is that heat is equals to ml. The m is 0.8 something kg. Let me check. 0.84 kg. And the specific latent heat of fusion is 64,000 joules per kg. So let me show you how I have done this numerical. Heat is equals to ml. M is 0.84 and the L is 64 kilojoules. So just multiply, this will be 53.76 kilojoules. So approximately 54 kilojoules energy is needed. So let me check the marking scheme. But the marking scheme has to say 54 kilojoules, or you can say 54,000 joules. So it's a 2-mark numerical, and I hope that you have understood. This was question number 3. Today we are doing October, November 2017 2-1 paper, and we are attempting the section A of this paper. So we are on the question number 4. Okay. So on your screen, figure 4.1 shows a mercury in glass thermometer made using a glass capillary tube. Describe how to check the 100 degree centigrade mark is in the correct position on the thermometer. So here he has marked 100 degrees centigrade here. So if you want to check this, if this mark is correct, this has been calibrated correctly. If you want to check that, the method is very simple. You will take water in a utensil and you will give it heat. And when it starts boiling, the steam of the boiling water will start coming out. Then you take this thermometer and hang this thermometer in that steam, not in the water. Hang it in the steam which is coming out of the water. And wait for some time. And then check the level of the mercury. Because the steam has a temperature of 100 degrees centigrade. So check the level of the mercury. If the level of the mercury coincides with the 100 degree centigrade mark on the thermometer has been calibrated correctly. If the level of the mercury, when the thermometer is in the steam of the boiling water, if the level of the mercury do not coincide with the 100 degree centigrade mark which is on the thermometer, it means that the calibration is not correct. So it's a 3-mark question, and I hope you have understood my description. Now let's see what I have written in the answer. So okay, so on your screen, question number 4, A part. With the help of a stand, hang mercury thermometer above a beaker which contains boiling water. Make sure that the atmospheric pressure is 1 atmospheric pressure. If the thread of the mercury becomes steady with a position coinciding with the 100 degree centigrade mark on the thermometer, it will show that the thermometer was correctly marked for steam point. So you can write this one, or you can write the way I described. And now let's check what the what the marking scheme has to say. Question number 4A part, use of boiling water. Thermometer in the boiling water or in the steam above the boiling water. Mercury level at 100 degree centigrade mark, or use of pure distilled water or at a pressure of 1 atmosphere. So my answer which I wrote and the answer which I described, they both are matching with the marking scheme, so there's no problem. You can write them. Okay, so let's move to the next part. Some thermometers contain ethanol instead of mercury. A second glass capillary tube is identical to the tube in the figure 4.1, except that it has no markings on the glass. This tube is used to mark an ethanol in glass thermometer. The volume of the ethanol in this thermometer is equal to the volume of the mercury in the thermometer in the figure 4.1. The thermal expansion of the ethanol is more than that of the mercury. State and explain how the maximum possible range of ethanol in the glass thermometer differs from the range of the thermometer in the figure 4.1. You see, because the ethanol expands more and the length of the mercury is same, and the volume of the ethanol and the volume of the mercury is same, but the ethanol expands more as compared to the mercury. So now in the same length of the thermometer, the range of the ethanol thermometer will be less than the range of the mercury thermometer. The range will be less for the ethanol thermometer. Let's check my answer and let's see. Because the ethanol expands more, so with a smaller change in the temperature, it will reach the end of this thermometer. So the range will be smaller. Range of the ethanol in glass thermometers will be less than that of the mercury in glass thermometer. As ethanol expands more, then mercury ethanol will reach end of the thermometer at a lower temperature than the mercury, because it expands more than the mercury. It is given in the question that the ethanol expands more than the mercury. Okay, so let's check the marking scheme. He says, question number 4B part, range is decreased or smaller or reduced, and he says ethanol reaches the thread reaches the end at a lower temperature because it's expanding more. So that's it. Question number 4 is done. Now we will move to the question number 5. Some medical processes involve the use of ultrasound. A part is explain what is meant by ultrasound. So you see, ultrasounds are sound waves whose frequency is more than 20,000 hertz and they are inaudible to human ear. We cannot hear it because the frequency of the ultrasound is more than 20,000 hertz. So let me go to my answer. Ultrasounds are sound waves which are audible to human. Frequency of the ultrasounds is more than 20,000 hertz. See? So this is out of the range of the human audible frequency. So that's why the human are not able to hear it. So the ultrasounds are okay. Let me check the marks. Pressure, vibrational, longitudinal wave of consist of compressions and rarefaction, or you can say sound waves. We said sound waves. Or inaudible sound. Frequency greater than 15,000 hertz to 25,000 hertz. So you can name any number here, but by book we say the frequency of the ultrasounds is more than 20,000. Next part. Explain briefly how ultrasound is used in the prenatal scanning. So you see, we have when we are doing the prenatal scanning, what we do, we have ultrasound emitter, and it also has a detector with it. So we send the ultrasound pulse, and it goes and it can pass through the tissues. And whenever there is a change in the density, for example, when it goes inside the body, and it will find, obviously you have different tissues, different organs, where there will be the fetus in the womb, and when there will be a difference in the density of the tissues. So what will happen from that boundary? Some ultrasounds will be reflected back, and when they come back, the detector, which is with the emitter, that will be able to detect them. And with the help of the computer, due to by using the sent ultrasounds and the received back ultrasounds, and by looking at their intensity, the ultrasound which came back, the computer can generate an image of the fetus. So this is prenatal scanning. Okay. So without actually opening, without cutting the body, without doing the surgery, without opening up actually the body, the doctor is able to see inside the body at the fetus. Let me show you my answer. So this is question number 5B part. Ultrasound pulses are sent into the womb of a pregnant woman via a transmitter. By measuring the time taken for the ultrasound pulses to be reflected, the depth of the reflecting surface within the womb can be derived and an image can be formed. And this happens with the help of a computer. This is not done manually. Okay, let's check the marking scheme. Ultrasounds transmitted into the body. This is one mark. Echoes reflection from the body or the fetus. That's one mark. And the image is produced. That's one. So very simple, 3 marks. I hope that you have understood and you will be able to write this answer. So that was question number 5A and B part. Now let's move to question number 6. This is that optional questions. It has the question number 6 will have 2 different parts. One will be from the regular physics and the other one will be from the electronics, and then there will be an option between them. The main part of a cathode ray oscilloscope consists of a glass tube. At one end of the tube, electrons are emitted by a hot metal filament. State 2 requirements for there to be a continuous flow of electrons in the tube. So in the cathode ray tube, the electrons will travel, they will start moving from the electron gun towards the screen. So if you want a continuous flow of electrons, so what are the 2 basic requirements? One is we have to put an anode there, a positive anode there, which is on a very high voltage, and it can attract those electrons. So I need a high voltage anode. I need electric field so the electrons can move from the electron gun to the screen. Another important requirement is that the gas pressure inside the tube should be very low. The reason is because you see, when the electrons are traveling, when they collide with the molecules of the other gas particles, because the gas particles, their size might be very large and the electron size is small. So when it collides with them, it might be stopped. So the gas pressure should be lower in the CRO tube. So let me check what I have written as answer and then we will go to the next part. This is question number 6. Okay. So question number 6, first part. Anode at a very high voltage. Anode is positively charged. Vacuum in the CRO. So very low pressure, or you can say we need a vacuum in the CRO. Let's have a look at the marking scheme. Question number 6A part is going on. Positive potential, high positive potential. Yes, we have written this point. Very low gas pressure, we have written this point. Heat filament continuity, this point is also good. A microphone detects 2 pulses of the sound. The output is displayed on the screen of an Oscilloscope. The figure 6.1 shows how the voltage output of the microphone varies with the time. Describe how the time taken between the two pulses can be determined using the display on the screen of the oscilloscope. Okay. So the first pulse shown on this left side, that is the real pulse which you sent. And this smaller pulse is the pulse which is the echo which came back, the reflected one. So I know the difference, I know the time between them. If you know the time between them and you know the speed of the pulse, if you know the time taken, let me reduce the size so you can see the whole thing. So you see, if you know the time between the original pulse and the reflected pulse which reached you, you know the speed of the pulse in the human tissues, then very easily you can find out the distance between between the emitter in your hand and the object from where the reflection took place. Now, the question is describe how the time between the two pulses can be determined using the display on the screen of the oscilloscope. You see, if you want to find out this time between these pulses, just count how many deviations are between the original pulse and the reflected pulse. And then multiply it with the time base. On the CRO screen, on the CRO, we have a time base that is the scale for the x-axis. Scale for the x-axis means that on the display, one small square, one small deviation represents how many seconds or how many milliseconds. So the method is very simple. You just count the distance between this horizontal distance, just count how many squares are there from this original pulse and the reflected pulse. And then you can multiply it with the setting on the, you can call it y time base. Time base means the scale for the x-axis, and you will get the time, actual time. It's a 2-mark question. I explained how this is used to find out the distance. Determine distance number of squares between the pulses. On the display, count how many boxes are from the the original pulse and the reflected pulse, and multiply by the time base. Time base is basically the scale for the x-axis. On the x-axis, the time is represented, so the scale for the time x-axis, that is called the time base. So just count how many squares are there between the original pulse and the reflected pulse, and then multiply it with the time base. That's it. Okay. This is the question from the electronics. He says many electronic and digital circuits include logic gates. The many electronic and digital circuits include logic gates. The NAND gate is the type of logic gate. In space below, draw the circle symbol for a NAND gate. You see, the NAND gate is basically the AND gate, and its input is fed into a NOT gate. AND gate plus the NOT gate. When you join them, that is called the NAND gate. So the AND gate and the NOT. I have drawn this on a paper. Let me show you. So here you have, there are two ways to draw this. One is, first of all, I draw an AND gate, and then the output of the AND gate is fed into the NOT gate. So you can write AND and then NOT, and that will mean NAND. Another way of doing this is that here I have AND gate, and at the output of the AND gate, we put a small circle. This small circle, when put on the output, that it means here a NOT gate is adjusted. So these are the two ways in which you can represent the NAND gate. Both these ways are good. You see here the symbol of the NAND gate, AND gate is shown. What's the next question? The two input terminals of the NAND gate are connected to zero voltage logic state 0, and no energy is supplied to these terminals. The output of the NAND gate is connected to an LED emitting light emitting diode. The output is not zeros. It has a logic state of 1, and the LED is glowing brightly. Energy supplied to the LED by the NAND gate state where this energy comes from. The energy basically is coming, this is an electric energy. So it's basically coming from some battery or some source of electricity or some source of EMF. Let me show you my answer, and then we will. He says that the NAND gate is connected to a battery. Let's check the markings here. The NAND gate has a power supply, battery, or it has an active device. Okay. Okay, so he says complete the truth table for a NAND gate. So here we have to write the truth table. In the truth table, this is basically AND gate, and then we have to invert the answer. So AND is like multiplication. In Boolean algebra, it's like multiplication. So try to learn how I will get the NAND gate's output. 0 multiply 0, the answer will be 0. And then you invert it, it will be 1. So I will write 1 here. So 0 multiply 1, the output will be 0. And then invert it, it will be 1. So 1 will be written there. So 1 multiply 0, that will give you 0. But when you invert it, the answer will be 1. So when you multiply 1 with 1, 1 with 1, it will be 1. So when you will invert it, it will become 0. So here I will write 0. I have written this truth table. So let me explain you again. And is like multiplying the inputs. It's like multiplying. So 0 multiply 0, the answer will be 0. But you have to then invert it. So 0 when inverted will become 1. So the output will be 1. 0 multiply 0, answer will be 0, but you invert it, the answer will be 1. 1 multiply 0, the answer will be 0, but when you invert it, the answer will be 1. So 1 multiply 1, the answer will be 1. When you invert it, it becomes 0. So this is how I have made this truth table. Hopefully you have understood. So let's move to the marking scheme so you can understand. 0 multiply 0, that's 1. Okay, 0 multiply 1, that's 1. 1 multiply 0, that's 1. And 1 multiply 1, that will be 0. Remember, this AND gate means that you multiply the inputs. Okay, A multiply B, and then we inverted the result. So that was, my dear students, question number 6, and we are done with this. So on your screen, we have question number 7. An electric circuit consists of a battery, a variable resistor, and connecting wires. Section PQ and the QR of the connecting wires are in a region of space where there is a uniform magnetic field. In the figure 7.1, the shaded area represents the magnetic field, and this magnetic field is represented with the crosses. When it's represented with the crosses, it means that the magnetic field is going into the page. We are looking at these arrows from behind, so it means that the gas is or the magnetic field is into the page. So in the figure sample 1, the shaded area represents the magnetic field. So here we have connected it with a DC power supply, and this portion of the wire QR and another portion of the wire SPQ and QR. The direction of the magnetic field is into the page. A current carrying wire in a magnetic field can experience a force. Yeah. So in the table, mark one tick in each column to indicate the force on the PQ and the force on the QR. So PQ. So this is conventional current coming from here. So the current is going in this way from P to Q. So let's apply. Magnetic field is into the page. I'm applying the left hand rule. Magnetic field is into the page. The current is conventional current is going from P to Q. My thumb is pointing upward. It means that the portion PQ will experience a force towards the top of this paper. You can see here I have written that the PQ a force towards the top of the page. So I hope you can understand this is how I have done. I have found the force in which direction the force will be acting. Okay. So for PQ, a force towards the top of the page. Yes. Put a tick here. Okay. You can put a tick here. Then on the side QR, let's decide for the QR. Okay. We will apply the left hand rule. The magnetic field is into the page. The current is going towards the bottom of the page from Q to R. My thumb is pointing towards the right side. This is a force. This is the magnetic field into the page. And this is the current. Positive to negative. My thumb is pointing towards the right side of the page. No, this is not the right. Yeah, this is the right side. So the force on the QR. A force towards the right of the page. I think this is the answer. Let me show you my working. I've done this. Yeah. We are right. A force towards the right of the page. So that's the answer. So one tick is here. Top of the page. One tick is here. And one tick is here. Let's check the marking scheme. What the marking scheme is today. Okay. So that's question number 7A part, the PQ, a force towards the top of the page. Second box ticked. And the QR, a force towards the right on the page, bottom box ticked. So very easy question. You only have to use the left hand rule. A battery in the circuit figure 7.1 is reversed. Straight and explain the effect of this on the PQ and the QR. Okay. So if I will reverse the battery, it means the negative will be here, the positive will be here. Now the current will be coming from this side. So let's check what will happen with the QR. Now the direction of the conventional current has changed. FMC. The magnetic field is into the page. The current is going upward. My thumb is pointing to the left. So the QR will move to the left. For the PQ, the magnetic field is into the page. The current is going this way. My thumb is pointing towards the bottom of the page. So the particles will move to the bottom of the page. Let me show you my working. You are using left hand rule, okay? So you need to be good at the left hand rule. When current will reverse, the direction of the force on the PQ and the QR will also reverse. On the PQ, direction of the force will be towards the bottom of the page, and force on the QR will be towards the left of the page. Okay?
Okay.
Okay, so question number 7. We are done with this. A variable resistor is adjusted and the current in the circuit decreases. So just one effect of decreasing the current. When you will decrease the current flowing through these wires, the force which is exerted on the sides, that will also decrease. The force which they experience, that will also decrease. Let me show you. Let me show you first one. Force experienced by the PQ and the QR. The force experienced by the PQ and the QR will decrease, will become small. Okay. So let's move to the next part. Question number 8. A sample of radioactive isotope radon-2222 decays by emission of alpha particles. As alpha particles travel through air, the air is ionized. Describe composition of an alpha particle. You know, alpha particle is like the nucleus of helium, and in this nucleus of helium, we have 2 protons and 2 neutrons. We have 2 protons and 2 neutrons. That's the alpha particle. It has positive charge on it. I've written this answer. Alpha particles are like nucleus of helium. It has 2 protons and 2 neutrons. So hopefully you can write this answer. Very simple. Forward question. 2 protons and 2 neutrons joined together. Very simple question. Okay. Explain how an alpha particles ionizes the air. You know, the alpha particles, their size is big and they have positive charge on them. So when they are moving in the air, they collide with the air molecules and they can hit the electrons, and those electrons will be kicked out of those atoms. And that's why what will happen when the electrons are gone out from an air molecule, it will convert into its ion, and that's why we say that the gas and the alpha particles have ionizing ability. Alpha particles are positively charged. It has affinity for electrons. So when it passes through air, it pulls electrons from the molecules of the air. Or when it collides with the air molecules, it knocks out the electrons from the other air molecules. So question number 8, first part, A, first part, 2 protons and 2 neutrons joined together. Question number 8, second part. One number is for saying it is positively charged, and the second number is for saying it pulls electrons from the molecules of air or knocks electrons from the molecules of air or gains electrons from the air molecule. I hope you can write this answer. State how the relative ionizing effect of alpha particles compare with that of the beta particles. So the ionizing ability of the alpha particle is more than the ionizing ability of the beta particles. And when you compare it with the gamma rays, alpha particles ionizing ability is very high as compared to the gamma ray. So beta particle and gamma rays both have lower ionizing ability. Let me check the marking scheme. One stronger and two strong. So means its ionizing ability is stronger. Okay. So alpha particles are positively charged, has affinity for electrons, this I heard. So when it passes through air, it pulls electrons from the molecules of air. Alpha particles have stronger ionizing effect than the beta particles. Alpha particles have stronger ionizing effect than the gamma rays. Okay, so next question. The half-life of a radon 222 is 3.3 x per 5 seconds. 3.3 x per 5 seconds. The number of radon 222 atoms in the sample is 4.8 x per mile x per 4. Determine the time it takes for the number of radon 222 atoms in this sample to decrease to 1.5 x per 6 x per 3. Sorry. So originally you have this much, and the half life is given, that's 3.3 x per 5. So let me show you my work. So in the start, this is the amount of energy we have. How much is this? 4.8 x per 4. So then I will half it. One half life passes, half it. So for 4.8 divided in x per 4 divided by 2, so it will become 1.2 x per 4. Then further divided with 2, 1.2 x per. First it was 2.4 x per 4. Then 1.2 x per 4. Then 6 x per 3. Then 3 x per 3. And when you again half it, it will become 1.5 x per 3. So you can count how many half-lives have gone by. So it is 1 and 2 and 3 and 4 and this is 5. So basically 5 half-lives. So one half-life is 3.3 x per 5 seconds. So you multiply it with 5, you will get 1.65 x per 6 seconds. Okay, so let's check the marking scheme if our answer is right. Okay. So our answer 1.65 x per 6 seconds, that is right. And okay, let's start. The question number 8, third part. Suggest one reason why in practice the time for the number of radon 222 atoms to decrease to 1.5 x per 3 may differ slightly from the value obtained in the figures in the B first part. The reason is very simple. You see, the radiation is a random process. It's a random process. So we cannot exactly tell when it will decay, how much it will decay. It's a random process. So let me show you my answer. Decay is a random process. A simple answer. So after this, the section B will start. So my dear students, today we have done October, November 2017 paper. This is a 2-1 paper. This paper belongs from the zone 1. In this session, in this video, we have done only the section A of this paper. The section B of this paper, I have already done, uploaded in the YouTube channel. You can find it, section B. You know, this lecture I am recording again. I've already done this October, November 2017 2-1 section A paper and uploaded in the YouTube. And there are a lot of views on it, and a lot of people have appreciated that also. But I made a slight mistake in that in the question number 1. So that's why now I have recorded this lecture again, and I will upload this in the YouTube channel. Both these papers will be there. You can find them in the YouTube channel. So if you find this video helpful to you, if you find that this video is helping you and it is improving your grades, so kindly subscribe to my YouTube channel. Also recommend your friends these videos so they can also improve in the physics, especially for the upcoming Cambridge exams. So I think that enough for today. And my dear students, thank you very much, everybody. It was lovely meeting you. Have a good day and God bless you all.